Here we're going to look at diffraction. Key thing is to be able to explain what diffraction is. We're going to be able to differentiate between single, double slit and diffraction grating patterns, as well as analyse the diffraction of a wave by a single slit, a double slit and a diffraction grating. So first up we've got to look at Huygens Principle. He suggested that each point on a wavefront should be considered as a separate source of energy called a wavelet, and the energy propagates out in a forward direction from each of these individual points. So if we imagined a wave here with a number of wavelets on the front, if this passes through a gap, the wavelets at the edge are going to start to bend. As they begin to bend, they interfere with the other wavelets and the waves superpose and you get diffraction, which you would have seen at GCSE. So from this diffraction, we get a diffraction pattern. So for a single slit, we get something that looks a little like this. We have parts where the waves come together in phase, so we'll get a bright fringe, and parts where they come together completely out of phase by 180 degrees or pi radians and cancel each other out, so we get a dark fringe. In the center, we get this maxima, so this really bright point. So if we imagine the wave travelling through the gap here, if you imagine the wave travelling from point 1 to y, that is going to arrive first because it's got the shortest distance to travel. Then 2, 3, etc. If we imagine and draw out the waves from each of these points, we get something that's a little messy. However, we can pair up these waves and show that they interfere constructively and destructively. So 1 and 4 will cancel each other out, 2 and 5 will cancel each other out, and 3 and 6 will cancel each other out. That means at y we should have no light, so a dark fringe. So if we zoom in a little and we imagine points of light coming from 1 and 4, these are the two, remember, that are going to cancel out and destructively interfere. If we look at the waves of light, they actually travel almost parallel to each other because the distance they're travelling is much greater than the slit width, so the slit that they've just travelled through. So we can draw a right angle triangle using half the slit and the two parallel lines. So the distance between 1 and 4 is half A being the slit width. We've got a right angle here, which makes this length here half a wavelength. So we should be left with sine theta equals lambda over A, just using a bit of simple trigonometry. So if lambda is greater than A, sine theta can't exist, so the first minima won't exist. If lambda is roughly the same as A, the first minima and theta will exist. And if lambda is much smaller compared to A, theta will be so small that it is basically 0 and the wave will just pass straight through. This gives us our first condition for diffraction. The wavelength must be comparable to the slit width. So lambda must be roughly equal to A. Otherwise, we're going to get no diffraction. Now looking at double slit interference. So up until Young's double slit experiment, most scientists believed that light was made up of tiny particles. So Young's double slit interference started to show that light travelled also as a wave. So if we have a light source shining through two slits, the waves will travel through and constructively and destructively interfere, leaving us with bright and dark fringes. However, the double slit pattern wasn't that simple. It also combined the single slit pattern. So ideally, Young's double slit interference pattern would look something like this, with bright and dark fringes due to constructive and destructive interference. However, because the gaps in the screens can't be infinitesimally small, we're also going to get interference. So we're left with a combination of the single and the double slit interference pattern. Now, describing the fringes in terms of wavelength, we have to consider the interference that is going on. So in a bright fringe, we know that the light is arriving in phase, and at a dark fringe, the light is out of phase by exactly 180 degrees or pi radians. So for a bright fringe, the path difference, i.e. the difference between the paths travelled by the light to get to that single point, must be a whole number of wavelengths. Otherwise, the wave would not arrive at the same point and you wouldn't get complete constructive interference. So the path difference must be n times lambda. For a dark fringe, so for cancellation and destructive interference, there must be a whole number of half wavelengths, so n plus a half lambda. So for a double slit interference pattern, we have this relationship. The distance between the fringes, i.e. W, the fringe spacings, is going to be equal to the wavelength times the distance between the slit and the screen divided by the distance between the two slits. That will give us the distance between our fringes. Now the n that we've mentioned earlier here is simply the order. The first bright fringe is n equals 1, the second bright fringe is n equals 2, and so on. So to successfully diffract, we need to make sure that the light source is coherent. This means that there's a constant phase relationship and the waves have the same wavelength. That means it's the same colour. So the light that we generally use in Young's double slit experiment is a laser, as this provides a coherent light source. A common question is what would happen if you used a light of a different colour. So remember that wavelength determines the colour of the light, red being a longer wavelength and violet being the shorter wavelength. As the wavelength increases, so if you think about a red colour light, the fringe spacing is also going to increase, looking at this equation. If lambda increases, so is W. If lambda decreases, W will decrease. If we keep S and D the same, so remember that's the slit separation and the distance between the slits and the screen. So finally, diffraction gratings. Diffraction gratings are exactly what they sound like. It's a load of slits next to each other. Each piece of light that passes through each slit is going to be diffracted. So each slit diffracts light. The diffracted light, again, is going to interfere. We're going to have constructive interference in the same way I had before, and we're also going to have destructive interference. So if we zoom in, Q and P are our two slits in our diffraction grating. We've got our parallel beams of light travelling through here. We've got our angle of diffraction here, and n times our wavelength here. N, remember, is the order. So using trigonometry, we're going to have sine this angle is going to equal the opposite, so n lambda divided by the hypotenuse, which is d. So we've got sine theta equals n lambda over d. You will need to know this derivation for the exam. So have a look at this diagram, make sure you understand it. So remember, D is the grating spacing. So the number of slits that there are going to be in 1 meter of this diffraction grating is going to be 1 divided by this spacing. Okay. The smaller D is, the more diffracted the light will be. To work out the maximum number of orders produced, so the maximum diffraction that happens, we substitute theta, so the angle of diffraction, for 90 degrees. And remember, sine 90 is 1. So to work out the maximum order, we do d equals n lambda, or n equals d divided by lambda.